Welcome to the Deep Dive. This is where we take those complex sources you send our way, research papers, articles, maybe even your own notes, and really plunge into them, pulling out the key insights for you. Today, we're tackling a really interesting corner of the AI hardware world. You know, for ages, NVIDIA's kind of been the default choice, right? A lot of that is down to their CUDA software platform. But the question is that dominance really set in stone? Because Intel's definitely making a push with their Gaudi neural processing units, their NPUs, and the source we're digging into today is perfect for this. It's a very detailed research paper, really gets down to the silicon level. It's reference 2501.0002110v2.pdf. It does this ground-up comparison of Intel's Gaudi-2 chip against NVIDIA's, workhorse, the A100 GPU. And crucially, it's focused on AI serving.
Yeah, and serving is the word here. It's often quite different from AI training. Training is like, building the model's brain. Serving is putting it to work, answering queries, making predictions, usually needing really fast responses for potentially thousands of users. Low latency, high throughput. What's great about this paper is it doesn't just stop at the headline specs, the marketing numbers. It really gets into the nitty-gritty performance details and, crucially, how easy or maybe how hard it is for developers to actually unlock that performance.
Okay, right. So let's unpack this challenge to the CUDA moat, as people call it, and see what this paper found that's really relevant for you. What makes Gaudi noteworthy, according to this research? What did they highlight?
Well, a few things stood out. First, Intel actually offers its own native programming system for Gaudi. It's called TPCC. It's meant to give developers that low-level control, kind of like CDA does for NVIDIA. Intel also, claims performance can be right up there, maybe even better sometimes. And maybe, importantly for the researchers here, the Gaudi chips are actually becoming available enough for this kind of independent, deep testing.
Got it. So our mission for this deep dive is pretty clear then. Cut through the hype, use this paper's rigorous evaluation, and figure out where Gaudi-2 really stands against the A100 for AI serving, both the raw power and the practical side of actually using it.
Yeah.
Okay, so the paper kicks off by putting the hardware head-to-head, just the basic specs. Gaudi-2 versus A100, what's the tail of the tape?
Right, so they lay out the key specs. If you look at the core AI math engine matrix multiplication, usually measured in BF16 precision, Gaudi-2's engine, the MME actually has a higher peak number. It's 432 TFLOPS versus A100's 312.
Higher peak for Gaudi on matrix math.
Okay, but AI isn't just matrix math. There's other stuff, vector processing, element-wise operations. And here, the A100's vector cores, its SIMD cores, have a much higher peak. We're talking 39 TFLOPS versus Gaudi-2's TPCs at only 11 TFLOPS. So a big difference there.
Okay, so A100 stronger on the vector side. What about memory?
Memory is interesting too. Gaudi-2 actually packs more capacity, 96 gigabytes versus 80 on the A100 version they tested. And the bandwidth is higher too, about 2.46 terabytes per second versus 2 terabytes per second for the A100.
More memory, faster memory for Gaudi-2 then.
Yep, and that communication, for linking multiple chips. Both have pretty hefty connections, around 600 gigabytes per second aggregate bandwidth, but they use different tech. Gaudi uses RoCE, A100 uses NZLink.
Okay, and power draw, that's always a factor.
Right. Gaudi-2 has a higher listed TDP, thermal design power, 600 watts compared to A100's 400 watts. So on paper, potentially consumes more power at its peak.
Okay, so those are the specs. Useful context, but like you said, the real story is performance on actual tasks, right?
Yeah.
The paper dives into microbenchmarks next.
Exactly. They tested core operations. First up, GMM, general matrix multiplication. This is like the absolute heart of most neural networks. They threw different shapes of matrices at the chips, tall and skinny, short and wide, square. And this is where it got, really interesting.
Oh, what did they find?
The paper found Gaudi-2 didn't just have the higher peak TFLOPS on paper, it consistently beat the A100 in these GMM tests. And maybe more importantly, it achieved higher compute utilization.
Meaning it was using more of its theoretical power.
Exactly. On average, about 4.5% higher utilization, sometimes way higher, like up to 32% in certain cases.
Yeah.
And the paper digs into why, which is fascinating. It seems to come down to a unique feature of Gaudi-2's matrix engine, the MME.
Okay.
It has a configurable geometry. Think of it like having a wrench set where you can adjust the wrench head size perfectly for the bolt. The paper suggests Gaudi-2 can actually adapt its internal structure, how its processing units are laid out, to better match the dimensions of the matrices it's multiplying at that moment.
Huh. So it physically reconfigures in a way.
Well, logically reconfigures its internal data paths and computation layout. This lets it use its hardware more efficiently compared to a fixed design, leading to that higher utilization they measured, up to 15% better just from being configurable, they estimate.
Wow, okay. So takeaway number 1 seems to be, Gaudi 2 has this clever hardware design for matrix math, its core strength, that lets it not just be fast, but actually use its speed more effectively across different matrix shapes.
That's a great way to put it. That configurable MME is a key differentiator.
All right, what about the other calculations? The non-GEMM stuff, activations, element-wise things.
Right, so the paper used tests, kind of like the standard stream benchmark for memory bandwidth, but they were focused on Gaudi's other main compute unit, the tensor processing cores, or TPCs. They wanted to see how well they perform and how to program them.
And what stood out there? Any best practices for getting performance out of those TPCs?
Definitely. The paper highlighted 2 main things. First, you really need to align your data access. Accessing memory in chunks of 256 bytes seems to be the sweet spot for Gaudi. If you try to grab smaller pieces, performance really takes a hit.
Okay, 256-byte alignment. Got it.
And second, using a technique called loop unrolling, basically telling the compiler to process multiple loop iterations at once, helps hide latency. It keeps the TPC busy while waiting for data or instructions.
Makes sense. So align your data, unroll your loops. How did the performance compare then?
Well, when the tasks were limited by memory speed, memory bound, Gaudi 2 was slightly faster, which you'd expect given its higher bandwidth.
Oh.
But they also artificially made the tasks compute bound, increasing the amount of math per byte of data. And in those scenarios, the A100 pulled way ahead.
Because of those more powerful vector cores we mentioned earlier.
Exactly. That 3.5x higher peak vector TFLOPS on the A100 translates directly into much faster performance when the bottleneck is the computation itself, not the memory. We're talking A100 hitting like a 19 to 38 TFLOPS versus Gaudi's 5.5 to 11 in those tests.
Big difference when compute is the limit for non-GM. But what about efficiency? How well were they using their potential?
That was interesting. In terms of utilization, when pushed to their compute limits, Gaudi 2's TPCs were actually pretty comparable to the A100's cores. Both hit around 50% utilization for some simple ops, and nearly 100% for others like a triade operation.
Okay, so takeaway number 2. A100 has way more raw vector compute power, making it faster for compute-heavy non-GEM stuff. But Gaudi's TPCs could be programmed efficiently, hit good utilization, and have a slight edge when memory bandwidth is the limiting factor.
Precisely. Then they looked at memory patterns, specifically gather-scatter operations. This is crucial for things like recommendation systems where you need to pull scattered data, like embedding vectors, from all over memory.
Right, that random access pattern. How did Gaudi handle that?
It was a mixed bag. For fetching relatively large chunks of data, say 256 bytes or more, Gaudi 2 was competitive with the A100. Not quite as good, maybe around 64% versus 72% utilization, but in the same ballpark.
Okay, competitive for large random reads.
But for smaller chunks, less than 256 bytes, Gaudi 2's performance just tanked. Its utilization dropped dramatically, averaging only 15% for accesses of 128 bytes or less, while A100 maintained around 36%. That's a huge difference, like 2.4 times worse for Gaudi.
Ouch. So that 256-byte memory granularity really bites here.
It seems so. It strongly suggests the A100's memory subsystem, maybe its cache hierarchy or line sizes, is just much better optimized for these fine-grained, random memory accesses.
Okay, takeaway number 3. Gaudi 2 struggles significantly with fetching small, scattered pieces of data compared to A100, which could be a major bottleneck for certain workloads.
Definitely a key finding. And the last microbenchmark area was communication between chips' collective operations like all reduce, all gather, essential for multi-device models.
Right. How do they talk to each other?
Here, the paper highlighted a system-level difference. The Intel Gaudi 2 server they tested uses direct point-to-point links between the 8 chips. The NVIDIA DGX A100 server uses an NV switch, which acts like a central non-blocking hub connecting all the GPUs.
Oh, different network topologies. How did that impact performance?
It had a noticeable effect. Gaudi 2 performed well when all 8 chips were communicating simultaneously. It could utilize its links effectively. But if fewer chips were involved, to say only 4 or 2, the performance dropped off almost linearly.
Because they don't have access to all the links via switch.
Exactly. Those point-to-point links mean pairs or smaller groups don't get the full aggregate bandwidth. The A100 system, thanks to the NV switch, showed much more stable performance regardless of how many GPUs were communicating. The switch ensures pairs or groups still get high bandwidth.
Interesting. So takeaway number 4. Gaudi-2's interchip communication scales well when everyone is talking, but its performance degrades significantly for smaller communication groups due to its direct link architecture, unlike the more flexible NV-switch-based A100 system.
That sums it up nicely.
Okay, so we've got a good picture of the low-level strengths and weaknesses. Gaudi strong on matrix math utilization, A100 on vector math and fine-grained memory access, and different communication scaling. How does this all play out in real AI applications? The paper looked at Rexys and LLMs.
Yeah, good choices because they stress different parts of the hardware. Recommendation systems, Rexys, often mix matrix math with those memory-heavy embedding lookups we just talked about, hitting that potential Gaudi weakness. Large language models, LLMs, are mostly about huge matrix multiplications where Gaudi should shine, but they also have complex memory patterns like page attention for handling many users efficiently.
Right. So let's start with Rexys serving. What did they find?
Well, first, they noted the standard Gaudi software library, the SDK, had a pretty slow default implementation for the embedding part. So to give Gaudi a fair shot, they actually built their own highly optimized version using that low-level TPCC language.
Okay, so they optimized it. How did it fare then?
Even with their custom, faster version, when serving a Rexys model on a single-chip, multi-chip wasn't supported for Rexys in the SDK, they used Gaudi-2 generally trailed the A100. On average, about a 20% performance loss.
Slower. And what about power?
It also used more power to do the work, resulting in lower energy efficiency, about 28% lower on average, compared to the A100 for this workload.
And does this tie back to the microbenchmarks?
Absolutely. The paper links this directly back to that weakness in handling small, scattered memory accesses. The Rexys model tested relied heavily on those embedding lookups, especially with smaller data sizes, and that's precisely where Gaudi-2 struggled against the A100's more capable memory system.
Okay, so takeaway number 5, part 1. For Rexys serving, especially memory-bound types, Gaudi-2 currently lags A100 in performance and efficiency, likely due to its hardware limitations with fine-grained memory access.
That seems to be the conclusion, yes. But now let's flip to LLM serving. This is where the picture changes quite dramatically.
Okay, I'm listening.
For serving a model like Llama AB on a single device, the paper found Gaudi-2 was consistently faster than the A100, averaging about a 1.47x speedup, so nearly 50% faster.
Wow, okay. Faster. And efficiency. Give it its higher TDP.
Even better on efficiency, it was significantly more energy efficient, delivering about 48% more performance per watt on average.
That's huge. So why the big turnaround for LLMs?
It comes back to the hardware strengths. LLMs are absolutely dominated by those large matrix multiplications, GM operations. And that's exactly where Gaudi-2's configurable MME gives it that utilization advantage we saw in the microbenchmarks. This benefit helped in both stages of LLM serving. The initial processing of the prompt prefill, which is compute heavy, and the step-by-step generation of the response decoding, which is more memory bound but still involves GMM.
Interesting. And the power consumption.
Despite the higher peak TDP number on the spec sheet, the paper found Gaudi-2 only consumed about 1% more power on average than the A100 during these LLM tests. They speculated this might be due to very effective power gating, basically, turning off parts of the chip when they aren't needed, especially for smaller batches or requests.
Right. Okay, so takeaway 5, part 2. For single-device LLM serving, Gaudi-2 is a clear winner, offering substantial speedups and significantly better energy efficiency than A100, primarily thanks to its superior GMM performance and utilization.
Exactly, and it gets even better when you scale up.
Oh, how so?
When they tested serving a much larger model, Llama 70B, distributed across 8 devices using tensor parallelism, a common technique, the advantage of Gaudi-2 actually increased. The speedup compared to an 8-GPU A100 system went up to about 1.35x, and the energy efficiency advantage grew to 1.56x, so over 50% more efficient at scale.
And why does the advantage grow at scale?
This seems to tie back to that communication characteristic. Remember how Gaudi-2's collective communication worked best when all chips were involved? Tensor parallelism typically involves all chips communicating frequently, playing right into the strength of Gaudi's system architecture.
Got it. So takeaway 5, the final part. For multi-device LLM serving using techniques like tensor parallelism, Gaudi-2's performance and efficiency lead over A100 actually widens, leveraging its system communication strengths. Yeah, that's a really clear picture from the application tests. Gaudi looks very promising, maybe even superior for LLMs, especially regarding efficiency. But for Rexys, at least currently, A100 seems to hold an edge due to memory access patterns.
That sums up the performance picture well. But performance is only half the battle, right? The other half is, can developers actually get that performance? The paper looked into the programmability aspect too.
Right, the software side.
Yep.
How easy is it to optimize for Gaudi?
They explored this through 2 case studies. The first was that custom RESIS embedding kernel they built using the low-level TPCC language. Their experience showed that, yes, TPCC is flexible enough. You can implement sophisticated low-level optimizations like batching lookups across different tables. They managed to get competitive throughput compared to optimized A100 code when dealing with large embedding vectors.
Okay, so the low-level language works.
It works. But the fact that it still fell short for small vectors, despite their best efforts, reinforces the earlier finding. The limitation there seems to be the hardware's memory granularity, not a fundamental flaw in the TPCC programming model itself.
Okay, so takeaway number 6. Gaudi's low-level TPCC programming system is capable and flexible for optimization, but performance can still be capped by the underlying hardware architecture, like that fine-grained memory access issue.
Correct. The second case study looked at optimizing at a higher level, using PyTorch, specifically for that page detention technique crucial for LLMs. And this revealed a really interesting software challenge.
What was the challenge?
The paper points out that, unlike NVIDIA's CDA, where you can directly call functions to use the tensor cores, their matrix engines, from your low-level CDA kernel code, well, Gaudi's SDK, at least at the time, didn't allow direct programming of the MME matrix engine from within a TPCC kernel.
Huh. So you can't directly control the main math engine from low-level code. How do you use it then?
Mostly indirectly. You define your model in PyTorch, and then Intel's graph compiler tries to figure out how to map the operations, including the matrix multiplies, onto the MME and the TPCs. This makes optimizing something complex like page attention, which needs tight coordination between data movement, TPCs, and matrix math, MME, quite tricky. You're relying on the compiler to get it right.
It sounds like less direct control. Did they find a way to optimize it?
They did find a clever workaround, but it was at the PyTorch level, not low-level TPCC. They basically restructured how the memory pointers for page attention were organized. This change made it easier for the graph compiler to see the parallelism and pipeline the TPC data gathers with the MME matrix multiplications more effectively.
And did that workaround work?
Oh, yeah. It resulted in huge speedups for page attention on Gaudi compared to Intel's initial baseline implementation. We're talking factors of 7x up to nearly 56x faster for that specific part.
56x. That's massive. But how did it compare to A100?
That's the catch. Even with that massive relative improvement on Gaudi, the optimized page attention throughput was still only about 45% of what they measured on the A100 using its optimized library, vLLM.
So still significantly slower on that specific complex kernel.
Yes. But interestingly, despite this bottleneck in page attention, the overall end-to-end LLM serving performance for Gaudi, as we saw earlier, was still competitive or better than A100.
How does that work if a key part is slower?
The paper suggests Amdahl's law is at play. Page attention, while important, isn't the only thing happening. Gaudi's significant advantage in the other GMM-heavy parts of LLM serving was enough to compensate for the relative weakness in their optimized page attention implementation, leading to strong overall performance.
Right, the bottleneck didn't dominate the whole runtime. Okay, so takeaway number 7 is optimizing complex operations on Gaudi, especially involving the MME, currently requires more high-level workarounds due to software limitations, like no direct MME access from TPCC. You can get big gains over the baseline, but matching highly optimized NVIDIA libraries on specific kernels might still be tough, though Gaudi's GPU strength can often make up for it overall.
That's a perfect summary. And pulling it all together, the paper concludes that yes, Gaudi NPUs show real potential to challenge NVIDIA, particularly in AI serving. Their analysis suggests the CUDA mode isn't just about the CUDA language itself, it's more about the sheer maturity and breadth of NVIDIA's whole software ecosystem, the optimized libraries, the compiler, the tools that effectively bridge the gap from high-level frameworks like PyTorch down to the metal.
So based on this paper's deep dive, what are the key challenges Gaudi still faces in closing that gap?
Software maturity seems to be the main one. Specifically, that lack of a direct, low-level programming interface for the MME from TPCC kernels was a big point. Also, having more transparency and control over the graph compiler's optimization decisions would likely help developers. And on the features side, expanding multi-device support in the SDK beyond just LLM tensor parallelism, like enabling it for RESIS workloads, seems important too.
Okay, so connecting us back to the listener, if you're out there evaluating hardware for AI serving, what does this paper tell you?
It tells you Gaudi 2 is absolutely worth a serious look, especially if your primary workload is large language models. The performance, and perhaps even more critically, the energy efficiency benefits shown in this paper are compelling, particularly when you scale up. However, it also flags caution areas. If your workload is dominated by those fine-grained random memory accesses, maybe sort of recommendation models or graph analytics, or if you critically need mature multi-device SDK support for those specific non-LLM workloads right now, the A100 with its hardware advantages there and more mature software likely still holds an edge based on this study.
So it really depends on your specific use case and how much the current software supports it.
Exactly. Workload matters. Software matters. And the paper also points towards interesting future directions. Well, comparing Gaudi against other competitors like AMD's latest GPUs or maybe other NPUs entering the market, also evaluating Gaudi for AI training, especially at massive scale, hundreds or thousands of devices, which is a different challenge than serving. And they mention keeping an eye on completely new types of architectures like AMD's Strix Halo, which plans to put CPU, GPU, and NPU capabilities all onto one integrated chip. That could really shake things up.
Absolutely. So the battle for AI hardware supremacy is clearly far from over. This deep dive really shows that challengers like Intel's Gaudi are bringing different designs, different trade-offs to the table.
Yeah, it highlights beautifully that the best hardware isn't some absolute thing. It's this complex interplay between the silicon architecture, the software stack built on top of it, and the specific demands of the job you need it to do.
Which leaves you, our listener, with maybe this final provocative thought to chew on. As AI continues to evolve, where is the advantage ultimately going to lie? Will it be in specialized hardware like NPUs, hyper-optimized for AI tasks, potentially offering peak efficiency? Or will the sheer versatility and the decades of development behind GPU ecosystems maintain their dominance? Or is the real disruption going to come from blending these different types of processors, CPU, GPU, NPU together in novel ways on a single chip? Definitely food for thought. Thank you for sharing this really insightful paper with us, allowing us to take this deep dive today.